You know what the second best thing in the world is? Amazon Prime. You know what the first best thing in the world is? Using someone else's Amazon Prime. And I got another Airzuka, and I am pumped because we're going to use this in class and have Airzuka Wars. I don't know when, I don't know how, I don't know how exactly I'm going to tie that into science, but it's going to happen. But anyway, I'm doing a lesson, another one, third one, and basically I'm going to summarize the lab that we did. Happy snow day, by the way, if you're watching on a snow day. But I want to go ahead and talk about what we did with that one lab where we had the car. You see right here, here's a diagram. You got some pieces of tape, and you put down a piece of tape every so-and-so seconds. So in this example, you got put a piece of tape every 3, 6, 9, 12, 15, 18 seconds, and then you measured the displacement that the car had to each of these points. So a lot of you measured in centimeters, and then you came up with the table, and then you graphed it. So a lot of you came up with a graph that looked like this. Here we go. And with this graph, let me see 2D shapes. You had a pretty, for the most part, a pretty straight line. Now there's some times that it didn't look right, and there's a lot of different reasons for that. It could have been a bad battery that was wearing out, but for the most part, we can draw a line through these points and get a pretty straight line. So let's talk about this. On the x-axis, we've got time. So as time goes on, what's happening to our displacement? Well, the car is getting further away from where it started. Now remember, displacement is a measure of how far are we from where we started, and it's measured in some sort of distance. In this example, it's centimeters. So it's going at a pretty consistent rate. Between each point, it's not varying too much. So what does that tell us? Well, a straight line has a lot of significance when we're talking about a displacement in time graph. Now I want to remind you for a second about slope. Now let's see if I can draw a little bit. Now slope, as you may remember from math, is rise over run. Rise, wow, that's bad, over run. And so I want to ask you, what is our rise? Well, rise is what's on the y-axis, and that's displacement. We're measuring that in centimeters. So if we're talking about units, our rise is centimeters. If we're talking about the run, well, the run is the x-axis, and that's measured in time, and that's measured, the unit we chose is seconds. So we're talking about seconds. So the slope of our graph has units of centimeters per second. Now that may not seem familiar to you, but it sounds a lot like something else that we are very accustomed to, and that is what we measure speed in with our cars, so miles per hour. So on the numerator, we still have a distance. We have a unit of distance, and on the denominator, we've got some unit of time. Same thing up here, distance over time. Well, what's distance over time? Well, you're talking about how far am I going per unit time. What is that a measure of? That's a measure of speed. So our slope is a measure of speed. Now that's only true for a distance time graph like we have here. But our slope, what this is telling us is how far are we going per unit time. That's exactly what speed is. The slope tells us how fast the car is going. Now, let me ask you, is this slope changing or is it pretty consistent? Well, for this data, it's pretty consistent. The slope remains the same. It's not getting steeper. It's not getting less steep. It's the same, which means, is our car speeding up or slowing down, or is it maintaining a constant speed? Well, in this case, it's maintaining a pretty constant speed, and you may remember from setting the car down, it's not changing speed that much. It's going one consistent speed. So this would make sense. Our car is going the same speed. So very important to know is that the slope that you got here, from this point to this point, or any point, is a measure of the speed between those 2 points. All right, so let's take this a little bit further. I've got this scenario that we went over in class. Over here, we have another displacement time graph. Now, I know this is displacement because displacement is how far are you from where you started. Well, in this case, distance from home. Home is where we start. That's our origin. So this point right here is home. And then there's 3 scenarios here, and only one of them fits this graph accurately. Let's take a look at them. Scenario A, Tom took his dog for a walk to the park. He set off slowly and then increased his pace. At the park, Tom turned around and walked slowly back home. Okay, that's the first one. Tom rode his bike east from his home up a steep hill. After a while, the slope eased off. At the top, he raced down the other side. Well, that looks exactly like the hill that he would have went up here. So it starts steep, eases off, and then he races down the other side. So this looks like a picture of the hill. And then C, Tom went for a jog. At the end of the road, he bumped into a friend and his pace slowed. When Tom left his friend, he walked quickly back home. All right. What we got here is we need to recognize, and we're going to talk about how speed is the slope. If we're looking at this, that's a pretty steep slope, all right, compared to this one. So this slope is steeper than this slope, or greater. We could say it's greater, which means he's going to be going faster because remember, slope is speed. So in the scenario, he's got to be starting out fast and then slowing down. So which of those scenarios is he starting fast and then slowing down? Well, let's take a look. He took his dog for a walk to the park. He set off slowly and then increased his pace. Well, that can't be because over here it shows that he started off quickly and then decreased his pace because the slope got lower. So it can't be A. B says Tom rode his bike east from his home up a steep hill. After a while, the slope eased off. At the top, he raced down the other side. Well, that's a picture of what's going on here, but the graph is not a picture. The graph is showing us how far he is from home. So in this whole scenario, we know based on this graph that he's got to return home because he goes back to the origin. He goes back to where his distance from home equals 0. So does he ever go back home in this scenario? Tom rode his bike east from his home up a steep hill. After a while, the slope eased off. At the top, he raced down the other side. He's still getting further away from home. It doesn't say he ever goes back home. So that can't be right because in this scenario, in this graph, it tells us that he goes back home. Let's look at C. Tom went for a jog. Okay, a jog is a decent pace. At the end of his road, he bumped into a friend and his pace slowed down. Okay, so that makes sense. He's at a jog, so this should be sleeper than when he slowed his pace. So here he's going for a jog. Here he slowed his pace. He's still getting further from home. And then when Tom left his friend, he walked quickly back home. Well, that would make sense here because he's going back home. He's going closer to home. So this should be a negative slope. He's going back to the origin. And then he eventually does reach home. So it makes sense. This is his jog. It's a steep slope. Then he slows down. It's a gradual slope. And then he turns around and goes back home. This is the point where he turns around and he goes back home. So that makes sense. So it's C. All right, let's take a look at a couple more. We got 3 more scenarios to match here. So based on our first graph, let's not even read these yet. Based on our first graph, we know that he starts at home. Someone starts at home, goes away from home, turns around because they end up going back to home, and then it looks like this is a faster pace leaving home again. Over here, does he ever go back home? Does the person ever go back home? No, because you can see that it never goes back to 0. So this person is getting further and further away. And it looks like their speed is changing because the slope is changing. It's pretty steep here, and then it slows down a bit, and then it's steep here, and then it tapers off. All right, so in F, we know that the person never goes back home. In G, the person starts at home, goes up here, all right, has a pretty good pace, and then, wait, what happens here? The slope is 0 here. If the slope is 0, what does that mean about his speed? Well, it means that his speed must be 0 because the slope is the speed. So here he's in the same place for this whole time. And that makes sense because you can look at this graph. The distance from home that he's at is the same from this time to that time. So this must be a scenario in which someone is stopped for a while and then goes back home. All right, now let's try to match it. Jake skateboarded away from his house, gradually building up speed. He slowed down to avoid some rough ground again, but then sped up. All right, so this one, you got to know that he's changing speed. So it says gradually building up speed. Well, which one would that look like? All right. Also, this one, he's never going back home. So the only one that fits is F, but let's make sure that that makes sense. He's gradually building up speed. All right, the slope is increasing here. And then he slows down. All right, the slope is tapering off. And then he speeds up again. The slope increases. That makes sense. So 3 must be F. Let's look at this one, number 7. Bobby went out for a walk with some friends. He suddenly realized he had left his wallet behind. He ran home to get it and then had to run to catch up with the others. Okay, so he has to go home here. And he goes home and then leaves again. So which graph does he go home and then leave again? Well, this one he goes home but he doesn't leave again. This one he does go home and leave again. So let's see if this matches. He went out for a walk. All right, he's leaving his home. He's going out for a walk. He realizes he left his wallet behind and he goes back. All right, this makes sense. He goes back home. That's a negative slope. He's going back home. And then he ran home to get it. Or sorry, he ran to catch up with the others. So he's going to catch up with the others. And this is a steeper slope, which makes sense because over here he was walking. Over here he's running. And that means that his speed is greater because the slope is steeper. It's greater. All right, that makes sense. So the only one left is 1 must match G. Let's make sure that it does. Tom ran from his home to the bus stop and waited. Okay, that makes sense. This is a very steep slope. And then waited. Okay, keyword waited. That means he's in the same position for that same amount of time, or for that amount of time. All right, the slope is 0. He's waiting during this time. That makes sense. He realized that he had missed the bus, so he walked home. Okay, yeah, he's going back home. And this is a less steep of a slope than it was over here, which makes sense because he's walking here and he's running here. That makes sense. So this is what I want you to be able to do for a quiz or a test, is be able to identify what is going on here with a distance or displacement time graph. So it's important to remember that the slope of a distance time graph is the speed. That's not true of every graph, but for a distance or displacement time graph, the slope is its speed. All right, that's all I got for you today. Enjoy your snow day.